Welcome, thank you for joining. This is my first ever scheduled live stream where I'll be doing some software development on YouTube. I've made videos in the past, but it's been a few years since I've uploaded. My goal today is to get back in the groove of doing things with video, overcome my creative writer's block that has kept me from uploading these past couple of years, and have something scheduled that makes me accountable to put something out into public again. This should be pretty easy to implement. What I decided to do today is add support for the Oklab color space to my visualization software. And I'll talk a bit in a minute about what that means. First, let's take a tour of what you're seeing on screen while I'm working and what my work environment is for the visualizations that I've made for past videos as well. This window here is my terminal window. This is where I do all of my development. This is also where I've got the command line interface that I've demonstrated in the past with the code that I've written available for typing commands, and can play sound files. And the simple tones like sine wave. And the visualizations show up here in this window, which is my custom visualization software. This is what I use to render all the animations, or most of the animations in my previous videos. And then this window down here shows information from the visualization software that just helps me know if there's something going wrong. You can also zoom in on just the visualization software. This helps all of you guys see what's going on. Zoom in on the code window. I work with a really small pixel font, and streaming at 4K, it probably looks really tiny on your screens, but that's what works for me. I'll zoom into the code even more if anyone has any questions and wants to see something specific. For the most part, I'll be using this view where you can see the overhead image and the camera view and kind of everything that I'm seeing on screen. So what is Oklab Color? Why did I choose this for my live stream today? Oklab is a color space. You've probably heard of like RGB, red, green, blue. If you've ever done any graphics editing, you've probably seen some of this. Like you get a color wheel picker to choose colors for text, backgrounds, shapes, whatever. A color space is a way of turning what we see as color into numbers so that computers can work with them. Then you can have like probably 3 numbers corresponding, say, to red, green, and blue, or hue, saturation, and value, or luminance and 2 color channels in the case of Oklab. You have a number from, say, 0 to 1 or 0 to 255. So a color space just lets computers work with color as numbers. And when you're working with numbers, you can do all this other stuff you do with numbers. You can add, subtract, blend, and that's kind of the foundation of how computer graphics work. The benefit of the Oklab color space, as opposed to just red, green, and blue, is perceptual uniformity, which is a couple of long words to say it looks smoother when you blend between different colors. This is a Wikipedia article talking about the Oklab color space. This is one of the references that I'll be using today while I'm writing this code. We'll kind of go through a little bit of that. I've got a couple other references up as well. This cylindrical model section of another Wikipedia article that talks a little bit more about some of the math for converting between different color spaces that we'll use as well. And then the original post describing the Oklab color space. Let's kind of dive in a little bit more to the Oklab color space and look at some of the math that's going to be involved. And then I'll go into the code planning, like how I'm going to approach implementing this in code and where that code's going to end up. I don't know how well this comes through with video compression, but if you're looking at this top one with Oklab and this bottom one with HSV, you can see the Oklab one seems to stay pretty much the same brightness all the way across, but the HSV one gives bright, dark, bright across the gradient. So that's kind of the biggest benefit. So Oklab is a way of turning color into numbers. For red, green, blue, which is the native color space for computers, it's kind of hard for us to think, if I want orange or brown or pink or turquoise or whatever, what do I type in red, green, and blue to get to those colors? Color spaces like this one give us 1 number for brightness and then 2 numbers for color. Useful for entering colors is this LCH version, which puts the color wheel on a cylinder. So the top of the cylinder up and down is brightness. And then from the center to the outside is color saturation. So the center is gray, the outside is bold color, and you can go anywhere in between. And then the angle around the cylinder is the hue, the position on the color wheel. So those are the color spaces we're going to implement today, LAB and LCH. And there are probably going to be a few others that we have to implement on our way to get there. In particular, this one, XYZ. The math for a color space transformation is usually described as matrix multiplications, a more compact way of writing out addition and multiplication. The goals for this stream's coding portion are to write a function that converts colors to and from Oklab, and then use that conversion function to draw some gradients in the visualization software over here. As we go, we might add more checklist items as we discover more requirements to get us from our starting point to our goal. Okay, so I'm gonna dive in and start coding. So this is where we're gonna start. We've got this blank slate, got the references up. I like to do a sort of hybrid of test-driven development and ad hoc development. I don't strictly practice test-driven development, but I am going to write some tests first, especially for something like this where there's a very clear behavior and test data that we can use, like these test values here from the Oklab specification. But the reason I mentioned test-driven development is because I'm going to have the code open, but I'm also going to have the tests open as well, and we're going to be working on both at the same time. So then on this second terminal, run the tests. Now we've got to figure out how I want to structure this. What functions do I want to write? What function signature do I want to build more abstractions? I think what I want to do is start by copying those existing functions from my other projects into this project. I want to copy those other conversion functions into this project. We just need this HSV to RGB. So copy that, paste down here, re-indent. Okay, so we've got this HSV to RGB. Just put a quick test in for that. The function is called HSV to RGB. My first test for this can be if I send in hue 0, saturation 1, value 1, I should get red 1, green 0, and blue 0 out. Now we have a passing test for that function that we copied over, HSV to RGB. This is done. Nice. We've already finished 1/3 of our work. Now the project's just going to keep growing past us, so we're not actually 1/3 done. That's our first function. This is kind of our starting point. Let's go to our resources here. We want to just restate the goal. We want to go from Oklab to RGB. We also want to go from this OKLCH, which gives us like a color wheel with an angle, into RGB, and it seems like the process is going to be OKLCH to Oklab to something else, and that last one is probably RGB, but there might be another step. So that's what we've got to figure out from looking at the resources here. Converting from XYZ to Oklab. Let's just go ahead and implement this because we actually have test cases here that we can use. What I'd like to do is use Ruby's matrix class. So this needs to go in the gem spec. We want to add a release dependency. This is another Ruby gem that this Ruby gem is going to depend on, and this is going to be the matrix dependency. So this is add dependency matrix 0.4.2. So I save that file. Then come to the other terminal and then do bundle install. You can also just type bundle, it does the same thing. And now we have that matrix gem added. But we learned from reading the resources that we need to go from Oklab to XYZ. So we'll implement the conversion from XYZ to Oklab first and then do the inverse transform. And the matrix gem is really going to help us with that. We need to add a require line for it in our code so that Ruby actually loads the file. This is XYZ to Oklab, and our parameters are going to be X, Y, and Z. And we expect it to return the LAB colors. We also want Oklab to RGB. This is going to be LAB. There's also OKLCH. That's the color wheel one, LCH. And I'm going to come back and write comments on these in a bit. We probably also want RGB to Oklab. Now we're going to write the tests for this XYZ to Oklab function based on this table. But for this stream, I'm going to write one spec for each line of this table. So there's going to be some duplication of data, but that's okay. Usually tests, it's okay for them to be a lot more verbose as long as they're still easy to read and maintain. Okay, so we've got these to-dos. That's exactly what we were expecting. Let's get started then with the matrix math. So first thing is we have our XYZ coordinates here. We need these in a vector form. So we want XYZ equals vector XY. So we have M1 times XYZ. Let's store that matrix as a constant. We get this from here, copy paste this. Okay, those are two matrices. So first, LMS equals matrix 1 times XYZ. We are nowhere near what we were expecting, so let's see what's going on. When I copy pasted this, it went column first and then across the rows. So I just need to transpose this matrix. Transpose for matrix just means you turn columns into rows and rows into columns. We can see those values are within a few decimal points of each other, like 3 decimals. When you have a fractional value in a computer, there's a really good chance that you're not going to get an exact answer, so we need to do approximate comparisons. So the function I'm bringing in mbmath for is a rounding method that I wrote that can take almost any parameter, array, whatever, and round the values within it. And then we can compare those. Okay, now we're down to 7 failures instead of 8. By the way, it looks like my camera overheated and shut off, so I just have the overhead view right now. I'll turn that other camera on after it's cooled down. And now we're down to 4 failures, which means we've fixed those other test cases. So this function is actually done and working. So now we want to implement the inverse. So we need the inverse of these matrices, M1 inverse and M2 inverse. We'll just kind of follow this process here. There's a good chance I've got the wrong expectations in here. Okay, yeah. So I've got the wrong test expectations, kind of like I did before. So I'm just going to change that to 2 decimals of accuracy for this function for now. Awesome. So now we have conversion from XYZ to Oklab and Oklab to XYZ, and our tests passed. Now I want to do LCH and I want to do sRGB. Basically, the first column of the matrix is the XYZ values for a pure red color. Okay, so now I've got tests for XYZ to linear sRGB. Now I'm going to implement it. It is basically just one matrix multiplication. So we've got our XYZ to RGB conversion function implemented. Now let's head the other direction. Okay, so that is implemented, just simple matrix multiplication. A few more steps to go. We want LCH and LAB to RGB. We need to get a gamma corrected RGB value though. Let's add that function next. When we plug in the boundary value from the inverse function, we should get the boundary value from the forward function. That's how that should work. Our gamma correction function now works. Got linear sRGB to gamma sRGB. We're going to go the other direction. Okay, so our gamma correction functions work in both directions now as well. Last thing is the cylindrical conversion. So we've got our gamma function, we need the cylindrical function. We're going to look at the cylindrical model now. We're using Pythagorean theorem to compute the chromaticity and the arctangent to compute the hue angle if we're going from AB to CH. This is basically a conversion from polar coordinates to Cartesian coordinates. It's going to get a lot more visuals soon. This is kind of the drudge work of implementing all the math, and then we get to play with it. There we go. So LCH to lab, that's done. And now we'll just do the other way around. And that should do it. So that's everything we need to go from LCH all the way to a gamma corrected sRGB value that we'll use in my visualization software. I want to make pretty pictures now. So it should be like X, Y, Z, RGB. Missing A. What? Not what I was expecting. Like, this has to be like a degrees versus radians thing. It is. There we go. Circle in LCH. Yeah, that looks like a pretty good match, and I think that's a really nice smooth gradient. I'm probably going to be using this a lot in future videos if I do make them. Hopefully I do. That's our code that we wrote in this live stream. We've got Oklab color conversion all the way in from the cylindrical coordinates into sRGB. We wrote some code to plot a disk of the Oklab color wheel. I've got it spinning on screen right now in my visualization software. That's how code works. We started from nothing and got this on the screen just by reading some specifications and documentation. Yeah, that's it for this stream. Thanks for watching. I should play the theme song or something. Actually, no. I know Pythagoras. I don't know Pythagoras. I know the Pythagorean theorem. I'm gonna go eat some dessert or something because it's been a long stream.